to review what we did last week with calculating molarity, remember that the formula for actual molarity is equal to the number of moles of solute per liter of solution. And so we talked about how you make your solution and all of that. So you should be able to describe that process in detail. But then if we are not solving for molarity, but we're solving for the number of moles, we would just manipulate that equation to get moles by itself. So you would have the number of moles of solute is equal to the molarity times the number of liters of solution. So in this case, it does need to be in liters. And then the example says how many moles of sodium sulfate would be dissolved in 1.5 liters of a 0.24 molar solution of Na2SO4. So if I'm looking for the number of moles, that would be equal to my molarity of 0.24 times my number of liters, which is 1.5. And then when I plug in 0.24 times 1.5, what does that equal?
0.36.
This equals 0.36 moles of my solute, which is Na2SO4, sodium sulfate. So after calculating the number of moles, we have to remember that in lab, we don't ever actually measure moles. We don't have a way to do that, but typically we're able to measure grams. So if you know your substance, you can always go from moles to grams using what? If I said I want you to measure out 0.36 moles of sodium sulfate, how are you going to measure that?
Use the atomic mass on the periodic table.
Okay, which we call the molar mass. So we're going to use molar mass, and that will convert moles into what? Grams. So when I want to make a solution, so if I want to make it, meaning 1.5 liters of a 0.24 molar solution, the first thing I need to do is use that number of moles of sodium sulfate to convert to grams using molar mass. So I'm going to say step one would be convert the number of moles required to make 1.5 liters of 0.24 molar solution, which that's equal to 0.36 moles. Convert that into grams using molar mass. So I'm going to make my thing a little skinnier, change colors, just so you can see what that process looks like. So if I say convert it, your immediate thought should be that this is going to be a T-chart. So conversions are when you take your given information, so in that case I'll use my 0.36 moles of my solute, and in this case my solute is sodium sulfate, so Na2SO4. I need to convert that using a T-chart into grams of my solute, so moles would come to the bottom. That will cancel out, and I would get grams of sodium sulfate, Na2SO4, on the top. To go from grams to moles, that is my molar mass conversion factor. Moles is always going to be 1 because the number of grams that comes from my periodic table is always measured per 1 mole. So if I go back up in my notes to what we did last week, we actually calculated the molar mass for sodium sulfate already. So this one, the actual molar mass according to my periodic table was 142.036 grams per mole. If you don't remember how to do that, you can go back and watch the other video. You could watch any of the molar mass videos, or you're just adding up the numbers on the periodic table. So that was 142.036 grams of sodium sulfate. And then I would need to multiply that by 0.36 to be the number of grams that are in that many moles. So if I take that, so 0.36 times 142.036 That gives me 51.13296. I'm going to write that whole thing down, and then we'll talk about sig figs in a second. So 51.13296, I think is what it said. 296, yeah. Okay, that is the number of grams of sodium sulfate, Na2SO4. That number of grams is equivalent to 0.36 moles. As far as significant figures, make sure that you kept your sig figs consistent, through the entire process. So I'll go back to the given information that you had. I had 1.5 liters, that is 2 sig figs. I had 0.24 molar, that is also 2 sig figs. So my answer had 2 sig figs, even though we didn't talk about it, that had 2 sig figs, so that's correct. Then this that I used, still 2 sig figs the entire time. So what do you think I'm rounding this number to? Perfect. So if I round that to 2 significant figures, what would I call this? Just 51 grams. We've used our scales enough. Maybe you recognize at this point they usually have 2 decimal places. So that's why a lot of things that we do, if it's like a standard, I would round to 2 decimal places. If this were what I actually calculated, I probably would keep that just to keep it accurate. But if this were the question that only gave you this level of significant figures, that means that the precision that you need to use matches that. So 51 grams is good enough. Okay, so first step was convert the number of moles into grams. Did it. I have 51 grams. Now that I know how many grams it's going to take to make 1.5 liters of a 0.24 molar solution, what's my second step? So let's say you're standing in lab and I'm asking you to make me 1.5 liters of a solution that has a concentration of 0.24 molar. What would you do? The first thing you did was convert. Okay, great. Now what? Yes, my question is, what would you do next? If I gave you a task and said, I want you to make me 1.5 liters of a 0.24 molar solution, you have all the supplies available to you. Every single piece of equipment that we've ever used in chemistry class, you have at your disposal. How are you going to make this solution?
Measure out the liter.
Measure out what?
Measure out the solution.
Okay, what solution? I'm asking you to make the solution.
So you want us to make 1.5
Liters.
Weigh
Yes, weigh out what?
liters? 1.5 liters?
Liters is a volume, so I wouldn't weigh it. The grams of what? Of the solute. I would weigh out that number of grams. How many grams? 51. That's why I just calculated that. So if you calculated it, great. That's like a good first step, is to know how much you need to weigh out. But then your second step needs to be, of course, to weigh out that number of grams. So I'm going to say actually weigh out 51 grams of Na2SO4. If you wanted to be like super over the top extra, you could describe like, get a beaker, put a beaker on the scale, press tare, take the solute, and then weigh out the 51 grams of sodium sulfate. Okay? So I weigh out that many grams of sodium sulfate into an empty beaker. Okay? Side note is that I know that I put a lot of emphasis on we don't measure in beakers because our beakers that we have available to us are not accurate as far as their markings for measurement, and they're all relatively small. So assuming that A, the beaker is large enough, so is appropriate size, and has accurate markings. So we would measure into an empty beaker, but specifically the beakers that we have access to in our labs in general, we don't measure in because the markings are not very accurate. Do you remember that? Do you want me to show you what I'm talking about, or you're good? You want me to show you? We're good? Okay, so remember your beakers, they usually have a marking at like 100 milliliters, and then the next marking is at like 150, and then the next one's at like 200. So they're kind of graduated like that, they're marked, but if I asked you to measure exactly 150 milliliters, you're kind of guessing where exactly that 150 mark is. If I said measure 160 milliliters, you're completely guessing. There's nothing even close to that. So our beakers that we use aren't really rated for like measuring that kind of volume accurately, but they do make beakers with accurate markings. So beaker or whatever other container would have an appropriate size and accurate measurement markings. All right, so step 2 was actually weigh out that amount into the appropriate container. Good. What's step 3? What? Fill up to what?
1 liter.
Why 1 liter?
1.5 liters.
Fill up to 1.5 liters. So in the steps that we learned up here, we said to fill to the 1 liter mark because we were making a molar solution from a solute, but a molar solution would be 1 molar. And 1 molar equals 1 mole per 1 liter. 1 mole of solute per 1 liter of solution. So if we are making a molar solution, that's just the easy way to do it. We'd fill it up to 1 liter. But in this case, A, we're not looking for a 1 molar solution, and B, we've already identified we want a different volume of this. And so all of these calculations that we did were based on this amount. So if I want to get 1.5 liters, I don't need to do anything extra with this. This is the number that I would use to get 1.5 liters. So my step number 3 is to fill the container to 1.5 liter mark. Again, assuming that it's appropriate size and has accurate markings and is actually able to measure that. So we would not do this in our beakers, but somewhere in the world there exists the type of beaker that you would use for this. Typically, if I have to do something like this, I'm using a volumetric flask because the volumetric flasks, if you remember, are the ones that have, they're typically round bottom, so they look like this, and then a really long, skinny neck, and they've got just 1 mark. So we really don't use volumetric flasks as a class, but this is what I use when I make solutions because they're super accurate for getting the right measurement. And then that's it. And then I guess step number 4, fill it with what though? Fill the container to the 1.5 liter mark with water, yeah, with your solvent. Probably water. And then step 4, stir it. And then we did do these 2 already, correct?
Yes.
Okay, so this is from our notes on Friday. Just remember that typically when we're talking about our stock solution, this is going to be talking about the more concentrated. So the one that is stronger. And then you need to pay attention to how things are worded. So for example, this one gives me my volume, or sorry, my molarity 1. I'm looking for the volume. It tells me that's my stock solution. It gives me my molarity 2 and my volume 2, but sometimes the way that it's worded, it will ask you about like what happens when you add water. So if you are diluting a solution, honestly, I don't remember what I meant to put in these blanks when I made the notes, so we're just going to kind of fill it in with what I think makes sense. First, you're going to add a small amount of stock solution or the concentrated solution. So you'll add the small amount of your stock solution or your concentrate. Then you are going to add the difference amount of water. So the reason that I'm saying that is because if you were actually to make this and you have your stock solution, so I'll zoom in over here and draw like a little picture for us. So if I have my solution and it's really concentrated, I know this picture is going to be tiny. So super concentrated solution, we'll say that it's mixed in strong. That's my stock solution. If I wanted to dilute it, I'm going to show my container being bigger. I would put my small amount of stock solution into there. So we'll say, okay, that's my stock solution, my still strong one. But then to dilute it, I'm going to add some amount of water. And when I add just water, my result is that I end up with a higher volume or more less concentrated solution. So stock solution, add water, and the result is we'll have a higher volume of what we'll call the less concentrated solution. So you see how I got that? Basically, I'm trying to add this into words. I like it with pictures because I think it makes sense. Of course, all the solute is going to end up mixing in with the water to make it less concentrated. So the steps that I would take to dilute a solution are add a small amount of my stock or my concentrate. Then I'm going to add the difference. So I'm going to actually clarify that and say the difference between volume 1 and volume 2. You can just put that, you can say difference there, but I just wanted to be specific in my notes. So add the difference add that amount of water. So the way that that works is that your volume 1 would be this volume right here, so that's my volume 1. And if I pour all of that stock solution into this, this volume 1 is still volume 1. And then if I say that my new solution is going to be here, that's volume 2. So the difference between volume 1 and volume 2 is the amount of water that you added. So that's what I mean by the difference. So then the total amount of solution that you make will equal the volume 1 plus the volume of water So I said it's going to equal the number of volume 1 plus volume of water. That will equal more milliliters of solution. So I don't remember what I meant to write there. So I want us to just have written in here. No, we're good. Thank you. Have in here that you're going to have a higher volume or more milliliters of a less concentrated solution. So I think this is trying to get at the same thing. So if I go down to the next page for our example, it says 30 milliliters of a 1.0 molar stock solution of sodium carbonate is added to 70 milliliters of water. What is the concentration of the dilute solution? So what's happening is I have my concentrated stuff. So my volume 1 is going to equal 30 milliliters. My solution is 1.0 molar, so if I'm diluting it, common sense and basic logic will tell us that based on the steps that we take to dilute something, and knowing that my volume is going to increase, so my volume 2 is at 70 milliliters, will the concentration of my second solution, of my more dilute solution, will the concentration be higher, lower, or equal to 1 molar? Lower. Why? Because what? But why? Because you're adding water. So you have the same amount of solute dissolved in more solvent. So then to figure this out, oh, actually, no, I said this wrong. 30 milliliters of a 1 molar stock solution, sodium carbonate added to 70 milliliters of water. So volume 2 is not 70 milliliters. The amount of water you're adding is 70 milliliters. So this so if I have 30 milliliters to start and then I added 70 milliliters to it, what is my actual volume 2? Sorry, I messed that up. 100. So then I would solve this with our M1V1 equals M2V2 equation. My M1 is 1.0 molar. My V1 is 30 milliliters. My M2 is what I'm solving for, and my V2 is 100 milliliters. So again, that 100 comes from the way that this is worded, says that 70 milliliters, that doesn't say it's my second volume. It says that this much water is added to my initial volume. And then as far as liters versus milliliters, in this equation, the M1V1 equation, if you put milliliters into your equation, it will give you milliliters out in your equation. So as long as your units for volume match on both sides, it can be in either one, liters or milliliters. Both are okay. For molarity, they're just going to be in molar the whole time. So I'd take 1.0 times 30, which just equals 30. I would divide this side by 100 and then divide that on the other side as well. So my M2, my second molarity, is equal to what? 0.3. And your unit, if you're calculating molarity, is just capital M. That stands for molar. Then as far as significant figures, don't forget to look at it. So this has 1 sig fig, this has 2 sig figs, this has 1 sig fig, so my final answer should have 1, and it does. This one says, how much water would you add to the solution to make it? I don't remember what I meant when I asked that question. Like I said, I kind of forgot what I was going for here because this answers that question, 70 milliliters, but I don't think that's what I meant to ask. So we'll have read it wrong. Maybe, probably. Make the same mistake multiple times. Sounds like me. Then if I were to describe how to make this solution in detail, do you guys want to practice that? I'll give you a second. Write down the steps that you would take, exactly what you would do to make this solution. I'm going to pause the video real quick. So just to clarify, the solution we're trying to make is 100 milliliters, since that's my final volume. So 100 milliliters, so the solution, talking about 100 milliliters of a 0.3 molar solution. So the answer that we just got from someone was that we would calculate first the number of moles of solute, then convert your moles to grams, and then weigh out that number of grams, and then fill up until you have your 100 milliliters of solution, which makes sense if you have a solid solute. But that's not the situation that was described here. So I guess if I were to give you a question like this, I would be super descriptive about what I'm looking for in terms of like how you're starting. But if you're making this solution and what you're starting with is a stock solution, then your starting material is already a liquid. So you don't have to do anything by converting it like that. So in this case, if I were describing it, it would differ from the previous one that we did, again, because I'm starting with a solution already where I already have something dissolved in something else. Of course, this pen is always cutting out. Let me keep twisting. Better? No. Okay, there we go. So start with and measure out your 30 milliliters of 1.0 molar stock solution. Start with a clean, empty beaker. Sorry. So start with a clean, empty beaker and measure out 30 milliliters of 1.0 molar stock solution. After you do that, you would add 70 milliliters. So add 70 milliliters. In this case, it's okay to measure your water in a graduated cylinder. So measured from graduated cylinder. Because the volume of your solution already contains your solute plus your solvent. If you're adding 70 milliliters of water, there's no solute to take into account, so you don't have to worry about measuring it in the same container. And then at the end, you're done. That's it. Then you would stir. That's exactly what you had. You didn't volunteer your answer.
I'm scared.
It can be scary. So stir, and then what you're left with is that. So if it seems easy, it's because it is. So on your test, I definitely am going to ask you something along these lines. It could be that you're starting with the solution and you just need to add water to it to dilute it. It could be that you're starting with a solid solute. If that's the case, I will specify exactly that. I will say that the solute is a solid, and then that's when you need to measure out the number of grams. So it just depends, because in the solution, you've already taken into account the volume of both your solute and your solvent. And then the last thing that we're going to do is talk about mixing solutions that contain the same salt, meaning the same solute, and have different molarities. If they have different molarities, you need to take into account the amount of that solution at that concentration. So I'm going to skip giving you this at first just so that you can see what it's like in practice. So a question that I could ask you is something like, what is the final concentration of sodium chloride when 3 solutions are added together? First, we have 150 milliliters of a 0.25 molar concentration. I have 325 milliliters of a 0.400 molar concentration and 425 milliliters of a 0.5 molar solution. So the question is, what is the final concentration? So I'm going to abbreviate final concentration as my molarity F for final. And then we're still using the same foundational equation for this, which is that M1V1 equals M2V2. We're just going to adjust it a little bit so that we can take into account that we're adding all of these things together. So if I have 150 milliliters of a 250 molar solution being added to that, somehow in the equation, I need to indicate that they're being added. So I'm going to take my volume 1. I'm going to write it volume first and then molarity, since that's the way that it's listed. So that's the same thing as V1M1 equals V2M2, just for the sake of being consistent throughout the equation. So volume 1, I'm going to multiply that by my molarity 1, and actually for consistency, I'm going to call them A so that we can keep it straight. So volume of solution A times my molarity of solution A. Then I'm going to add to that the volume of solution B times the molarity of solution B. Then I add to that the volume of solution C times the molarity of solution C. So volume C times molarity C. When I add this plus this plus this, since those are all the things I'm adding together, that will equal my volume final times my molarity final. So I've already identified that the final concentration that it's asking me for, I'm going to call my final molarity, which means that that is the only variable that can be missing when I plug all of this into the equation. So it's important to note that volume is additive in the sense that if I add 150 milliliters of something plus 325 milliliters of something else, and 425 milliliters of a third thing, my final volume can be found just by adding those three things together, not taking anything else into account. So for my volume final, I have that value given to me basically by adding those together. So final volume is going to equal volume of A plus volume of B plus volume of C, which equals 150 plus 325 plus 425. So my volume final is going to equal what? What'd you say? 900. Perfect. And the reason I could just add them all together is because they were all in milliliters already. I could be tricky and give you something in liters and then ask you to convert it. You need to be paying attention to your units. So it's okay to keep this in milliliters as long as everything stays in milliliters the entire time. So then I would just go through and plug in all of the values that I have. So first I would take my 150 milliliters times 0.25 molar. So 150 times 0.25 plus 325 times 0.4 plus 425 times 0.5. And that would equal my volume final, which is actually 900, so I'm going to go ahead and just plug that in, times my molarity final. Then to get my molarity by itself, I would need to divide this side of the equation by 900. My 900s will cancel, and then I would divide this side also, also by 900. So take a second, calculate that, and then that will give you your final molarity. And while y'all are doing that, I'm going to just put our equation up in the box up here with something a little bit more generic, so I'll use 1s and 2s. I just don't want you to get confused with where they're coming from. So that's why I labeled them as A and B. You can always label any of your solutions whatever you want to label them. So for example, like in the top one, if you wanted to label these as like stock solution, you could do that. You could not, instead of calling it like 1, you can call it stock, and diluted versus diluted, as long as the correct solution is being accounted for in each place. So you would add all of them up together. If you have 10 different solutions, then you'll add all 10 of those solutions. and then it would equal your molarity final times your volume final. A lot of times I won't give you a final volume. You will just be expected to be able to calculate it based on what we did here. The fact that when you add all these different solutions together, your final volume is going to be the combination of all of them. And I'm also adding a note to remember that units in need to equal the units out. That means that it's okay to use milliliters for volume. Say milliliters or liters. So, okay to use milliliters or liters for volume as long as it's consistent. So you cannot switch units halfway through. However, molarity by definition will always be per liter. So your M is always going to be number of moles per liter. That's fine. You can put molarity and milliliters in the same equation if you're using it appropriately. So what did we calculate for our final molarity? Thought y'all got 0.42 repeating, right? Cool. So I would call that 0.42 and then double check your sig figs, make sure that everything is matching consistently. This has 2, this has 3, this has 3, 3, 3, 3. So my number of sig figs would be 2 significant figures, so that's good there. What's my unit? Just capital M for molar, good. Any questions on that one? Yes. No. Okay, so because the definition, I'm going to scroll back up so that we can see what I'm talking about. Not that. Because the definition of molarity specifically is the number of moles of solute dissolved per liter of solution, when you are using capital M for molarity, molarity is always going to be per liter, but that's built in to the units there. But when I'm multiplying molarity times a volume, the volume can be in milliliters. So the thing here has to be in liters. The denominator, if you are calculating molarity using this equation, has to be liters because that is the definition of what molarity means. But if you are given molarity, so if I go down here, that M tells me this is 0.25 moles per liter of sodium chloride. This tells me that this is 0.4 moles per liter of sodium chloride, and this tells me that it's 0.5 moles per liter of sodium chloride. So the liter portion is already taken into account in the unit that it's given to me in. So it's okay that I'm multiplying it by milliliters because that's not intended to cancel out. That's just your volume, and as long as you're consistent in each of the things that you're adding up and on both sides of your equation, you can be in either one. If you're not sure or you feel like you're not confident that you'd remember to switch it or whatever, you can always be safe by converting to liters. Like, that is definitely a safe bet. So if you're confused on that, you can convert them all to liters. Again, it just has to be consistent, so you need to keep liters on both sides. If this process seems familiar, it's because we did something very similar back in our gas laws unit when we did Boyle's law. We talked about having like a gas with a certain pressure at this volume and a gas with a certain pressure at this volume, and then putting them into a container at a certain volume and seeing what happens. So it is the exact same kind of calculation like that. Good? Yes?
I forgot to put the repeating symbol beside the 2.
I don't need to because I did 2 sig figs. All right, last question, and then we are completely done with our notes. Letter B says, suppose 50.0 milliliters of 0.250 molar cobalt 2 chloride solution is added to 25.0 milliliters of a 0.35 molar cobalt 2 chloride. probably supposed to say solution there. What is the volume of the solution when both of the solutions are combined? So if my equation, I'm going to highlight them in different colors. So we'll do blue first. So if I have 50 milliliters of that solution, and I have a different solution that is 25 milliliters of that one, when I combine them both, the first thing I can do pretty easily is find out what is my final volume. Actually, this whole question is super easy. That's all it's asking for. That is added to that. What is the volume of the solution when both solutions are combined? Just 75. So your volume equals 75 milliliters. So the concentration doesn't affect your volume at all. And since this is just asking for volume, it's saying if I add 50 milliliters of something to 25 milliliters of something else, what's the volume when I put them together? It's just the combination of both, so 75. To get this right, if I gave you a question that was this straightforward on the test, it would probably make you super anxious. Double check your sig figs. That's probably what I'm looking for. So this isn't the right number of significant figures for 75, but 50.0, that has 3 sig figs. 25.0 has 3 sig figs. So my final answer should have 3 sig figs, which would be 75.0 milliliters. Good. If you're adding them, actually, remember the sig fig rule was digits after the decimal, so you would round to the least number of digits after the decimal. So if I added 50.0 plus 25.0, that would still have 1 digit after decimal. So remember, it's not just a straight up sig figs thing, it's a digits after decimal thing. But that is it. So we will end there.